All right, so in this lesson, what I'm going to have you guys do is go 2 steps further with rational functions, and we're going to talk about end behavior, and we're also going to talk about intercepts, okay? So what you were supposed to do on Tuesday was you were supposed to find the horizontal asymptotes of the rational function, all right? So just to go back over that, when you do end behavior, you're going to pretty much do the same thing. You're going to find the horizontal asymptote, and then if it doesn't have a horizontal asymptote, then there's a little bit of extra work that you need to do. Okay, so what I would do right now, when you do your homework especially, is have the 3 rules out for horizontal asymptotes, because to do end behavior, you have to know if there's a horizontal asymptote. Okay. So if there's a horizontal asymptote, the end behavior is really easy. If there is no horizontal asymptote, then the end behavior is a little more difficult. So the first thing is, what is end behavior? Well, end behavior, and this should not say polynomials, this should say rational functions. I just had a chance to change it. So this should say the end behavior of a rational function tells you how the graph behaves as x approaches infinity, and how it behaves as x approaches negative infinity. Now, the reason I accidentally typed polynomials is because it's the same thing. The end behavior of a function, any function, is just telling you what the graph does when x gets really big and when x gets really small. So as x approaches infinity, that's going to be your right end behavior. And as x approaches negative infinity, that's going to be your left end behavior. All right. Now, when we did polynomials, there were 4 end behaviors: up, up, down, 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 up, and up, down. And rational functions can have one of those 4. Okay. However, rational functions can do one other thing, and that's why we have to study them a little bit differently. Okay. So if you think about a graph, and you talk about end behavior, when x approaches infinity, that'll tell you what the graph is doing over here. It might be going up, it could be going down, right? And then the left end behavior over at negative infinity is, maybe what the graph is doing over here. Okay, we can have something that might look like that. But the idea is we're going to write it in arrow notation. And in calculus, you will write it in what's called limit notation. This isn't scrolling, so give me 1 second. So we're going to write it in arrow notation, and in calculus, you'll write it in limit notation, which is 1 step past arrow notation. So step number 1, if you're dealing with a rational function, you want to first determine if there is a horizontal asymptote. If there is, the end behavior of the graph will go to the horizontal asymptote. So let me give you an example. If we have y equals x cubed plus 2x over x to the 4th plus 3, we know that this has a horizontal asymptote at y equals 0 because the degree of the numerator is less than the degree of the denominator. So what that means is, as x goes to infinity, y is going to go to 0, and as x goes to negative infinity, y is also going to go to 0. So if you have a horizontal asymptote, your right end behavior and your left end behavior will just be the horizontal asymptote. Okay? So if you have a horizontal asymptote, it's easy. You just say, as x gets big, y goes to the horizontal asymptote, and as x gets small, y goes to the horizontal asymptote. Okay? Now, step number 2, if there's no horizontal asymptote, then the rational function acts like a polynomial. That is not how you spell polynomial. And so you'll either get up, up, down, 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 up, or up, down. Okay? And the way you figure that out is not want to scroll. There we go. The way you figure it out is you simplify what you have, and then you determine which polynomial it is. So here's an example. Let's say we have y equals 3x to the fourth plus 7x squared. And then in my denominator, I have something like negative 2x plus 4. Okay? Now, since the degree of the numerator is greater than the degree of the denominator, there's no horizontal asymptote. Okay? And that would be your answer to part D on your homework. You could have just put that there was no horizontal asymptote. But when it asks for what the end behavior is, you then have to simplify this. So what we do is we look at the term that has the highest exponent in the numerator, because he's in charge. And then we look at the term that has the highest exponent in the denominator, because he's in charge. Okay? And what we do is we write those together. Okay? And then we simplify them. So it would be negative 3 halves, right? And then when you simplify variables, you subtract their exponents. So if you have x to the fourth over x, that would be x cubed. And then you go to your polynomial chart. So remember, this is a negative odd, right? And negative odds have end behavior of up, down. Okay? So now what we do is we just write that in arrow notation. So left side, as x goes to negative infinity, the left side goes up. So y would go to infinity. And as x goes to positive infinity, this side, right, because this is where x is getting big on the right-hand side, y is actually going down. So y goes to negative infinity. All right, so this is the end behavior of a polynomial, of a rational function that doesn't have a horizontal asymptote. It could be one of these four things. Okay? So if the polynomial does not have a horizontal asymptote, it's going to act like a polynomial. Okay? So if the rational function does not have a horizontal asymptote, it's going to act like a polynomial, and it will have one of the four end behaviors that we dealt with earlier with polynomials. So let me go through a couple of examples with you down here. That was not supposed to happen. Okay, so for this one right here, if you look at the highest numerator, or the highest degree up top, it's 5x squared. And if you look at the highest degree in the denominator, it's x cubed. So we have a situation where the degree of the numerator is less than the degree of the denominator. So we have a horizontal asymptote at y equals 0. So that would be the answer for part D on your homework. For the end behavior, though, we say as x goes to negative infinity, y is going to go to the horizontal asymptote. And as x goes to positive infinity, y is going to go to the horizontal asymptote. It doesn't matter what order you write these in, but if you want to go left to right, you would start with negative infinity. All right, for this one, we take a look and we find the highest exponent up top. It's 12x to the fourth. And we find the highest exponent in the denominator, and it's 6x to the fourth. So this is where the numerator's degree is equal to the denominator's degree. So then the horizontal asymptote is at the leading coefficient of 12 over the leading coefficient of 6. So we have a horizontal asymptote at y equals 2. So that means that as x goes to negative infinity, y goes to 2. And as x goes to positive infinity, y goes to 2. All right, now for the last one. This one's a little out of order, so just be careful. here's the term that's in charge up top because it has the highest exponent. And here's the term that has the highest exponent in the denominator. It's negative x cubed. Now in this case, the numerator's degree is greater than the denominator's degree, so there's no horizontal asymptote. Okay? So what we do is we take the term that's in charge up top, so the highest exponent, x to the fifth, and we compare it to the term. Now make sure you take the coefficient with it because it's negative. That's important. That's going to affect the end behavior. And that means that if we simplify this, we have a negative x squared. And that has an end behavior of down, down. So the end behavior of my rational function would be as x goes to negative infinity, y goes to negative infinity because it's down. And then as x goes to infinity, y goes to negative infinity. Again, down, down. Okay? So now what you're able to do is you're able to go ahead and complete the end behavior on your homework. So go back to 1 through 18. Sorry. And do the part that says end behavior in arrow notation. Okay? All right, so the last thing I want to show you today is how to deal with intercepts. And again, this thing does not want to scroll. Okay. For any function to find the x-intercepts, you just let y equal 0. That's for any function. So it's the same for rationals. And to find the y-intercept, you just let x equal 0. Okay? Now, some of these are going to be tricky, and we'll go over them the next time we have class. But for right now, just kind of, work through this. It's pretty self-explanatory. You're just going to find the x and y intercepts. The one thing I should mention is functions can have more than one x-intercept. In fact, there are functions that have an infinite number of x-intercepts. They're trig functions. But you don't have to have an x-intercept, but you can have multiple ones. For y-intercepts, though, you can have at most one. Okay, otherwise it wouldn't be a function. You don't have to have one for rational functions, but you can't have more than one. Otherwise, you would not have a function. Okay, so just kind of keep that in mind. The scrolling aspect of this is not fun. Okay, there we go. All right, so let's take a look at this. We're going to find the x-intercepts and the y-intercept. So to find the x-intercept, you just let y equal 0. Okay, so that's f of x. So we just say 0 is equal to, in the numerator, we have x minus 5 times x plus 1. And in the denominator, we have x minus 2 times x minus 3. So if we set that equal to 0, what we would do is we would multiply both sides by the denominator. Okay, so on this side, it would cancel. And if we multiply this side by the denominator, it's just 0 times the denominator. So obviously, that's just going to be 0 is equal to the numerator. And then we just use the zero product property. So we get an x-intercept at 5 and an x-intercept at -1. And the way you want to write your intercepts is as ordered pairs. So if we plug in 5, we get 0. And if we plug in -1, we get 0. Okay? So these are my x-intercepts. To get the y-intercept, you let x be 0. So we get f of x, or y, if that makes more sense to you, is equal to 0 minus 5 times 0 plus 1 over 0 minus 2 times 0 minus 3. So my numerator is -5 times 1, which is -5. And in my denominator, I get -2 times -3, which is +6. So my y-intercept, I plugged in 0, and I got -5/6. So that's my y-intercept. Okay, so these are my x-intercepts, and this is my y-intercept. Now, I can show you some additional examples, but in this one, if you're trying to find your x-intercept, you just get 0 equals, and then these are going to cancel, right? So you would get x squared minus 6x plus 9. So what I'm just showing you here is sometimes you have to factor it. So I get an x-intercept of 3, 0. Okay? If I'm at my y-intercept, I just let all the x's be 0. So in my numerator, I'd get 9, and in my denominator, I get -9. So my y-intercept is -1, so 0, -1. All right, that's a bit of a crash course, but you have all found x and y intercepts before, so I'm sure that you can handle it. Just give it a shot, and we'll go over it. So at this point now, you should be able to do every step on the homework. All right, so you're going to do 1 through 18, and I think it's A through G. But whatever all of the letters are, you should be able to do all of them now, okay? So what you're going to do is bring that with you to class on, I want to say Tuesday, but I'm probably wrong. Next week, I think Tuesday is an odd day. So bring that with you to class on Tuesday. You should have 1 through 18 done, parts A through G, okay? You're not turning anything in. I'm not giving you a grade on this right now. We're just going to go over it on Tuesday, okay? So if you have any questions, the best thing to do right now would be to email me, and I'll do my best to get back to you. But please take care, and I will see you soon.